How is it going? This is Mike coming back at you here with another video on discrete mathematics. In the previous video, we got an introduction into predicates, and then we talked about quantifiers and the three main types of quantifiers that we will see. Those are the universal quantifier, the existential quantifier, and then the unique existential quantifier. We talked about some quick cases about when those things may and or may not be true, and we talked about what these things mean. We gave a description of how to show whether or not each of these types of statements are true, but we didn't necessarily go through some samples. We're going to see those samples in this video here. So we kick off this video with a little bit more on predicates. So let X have the domain, which we typically symbolize by capital D, being Z, the set of all integers or the set of all whole numbers. And then we are going to define our predicate, P of X, to be 4X is greater than negative 11 halves. Now, something that you may or may not have seen, this right here, the colon and then the equal sign following it right after it, that's just a common symbol that you'll see being used to say that we are defining this thing to have this name. And we are defining the statement, or we are defining the predicate for x greater than negative 11 halves. We're giving this thing the name capital P of x. And we said that from our previous video, a predicate is a sentence with finitely many variables and is only a statement once you assign a value to the variable or variables inside of your predicate. Right now, as it sits, 4x is greater than negative 11 halves. That may or may not be true. That's based on what value of x we plug in. If I take negative 3 and I plug it in for x, then I get a false statement here, because negative 12 is not greater than negative 11 halves. If I take x equals negative 1, however, and I substitute it in for x, then that statement is true. Negative 4 is greater than negative 11 halves. So this is what we mean by a predicate containing variables, and we can only determine the truth value of that predicate once we substitute something in for the variables, or the one variable like we see in this case. Also, from our previous video, we said that we're mainly concerned about the values, the x values from our domain that make the predicate true, and we take all of those x values that make it true and we put them inside of a set. We write them using set notation. Now, for this particular predicate, we can come up with what are all the x values that will make this predicate true. You would just divide both sides by 4. And what you'd find is that every integer greater than or equal to negative 1 makes capital P of x true. So we can write all of these solutions inside of a set. So we have an open set bracket, the open squiggly there. And then I chose to write out all of these numbers: negative 1, 0, 1, 2, 3, 4, 5, so on and so forth, and then close it up with a closed set bracket. The other way that you could write this is if you did open set bracket, which is, again, the set of all x in our set capital Z, big vertical bar for such that you could say x is greater than or equal to -1. That's the other way that you could write this answer. That would also be correct. But either way is fine. That does not matter. Here's another sample problem. This one is a little bit different. In this case, our domain is a selection of words, not so much numbers. I did say we'd see a couple samples like this. So here is one such example. So let our variable x have the domain, which is 5 possible words: snow, orange, shower, blue, and red. And we're going to define our predicate p of x to be that x has at least 2 vowels in it. So, again, based on what x value we plug in from our domain into capital P of x may or may not be true. If I were to take the word snow and plug it in, then P of x would be false, because snow only contains 1 vowel. If I were to take the word orange and plug it in for x, then that would be true, because orange does have at least 2 vowels in it. It has 3. So, again, we look at all of the x values that would make our predicate true, all the x values from our domain, capital D, that make our predicate true, and we put all those guys inside of a set. So all the values that make P of x true here, and this is again called the solution set, is the set containing orange, shower, and blue. The other 2 words, snow and red, only have 1 vowel in them. So those are just a couple cases of looking at some some predicates. My apologies, and just providing a bit more clarity to see how the substitution of a value in for the variable does impact whether or not you get a true statement. Now we're going to go on and look at some samples with our universal, existential, and unique existential quantifiers. So for the next few sets of quantifiers that you will see, we're going to work with a common domain. Our domain is going to be the numbers -1, 0, 2, 3, 5, and 6. So I have 2 quantified statements here. They both contain that universal quantifier, the upside down capital A. Number 1 reads, for all x in D, x squared is less than 40. Number 2 reads, for all x in D, 3x is greater than 5. So as a recap of our previous video, we said that a universal statement, or a statement containing a universal quantifier, is true if and only if every x value in that domain, when you plug it into your predicate, makes it true. If there's at least 1 x value such that when you plug it into your predicate, it's false, then your universal statement is not true, and you have found a counter example. So counter examples are the guys that make universal statements false. So looking at number 1, saying for all x in D, x squared is less than 40. So what we want to do is for each of these x values, we're going to square it. We're going to see if that result that we get is less than 40. Now this is a very basic calculation here, and these are all going to be very basic calculations in this video. This is more about just letting ourselves get used to these quantifiers and seeing these things and understanding how to tell when a universal statement is true or not. So it shouldn't be any surprise, and it shouldn't take much work to figure out that the first quantified statement is indeed true. We can take each of the numbers in our domain, square it, and we get something that is less than 40. And there's a name for this process of taking every value inside of your domain, plugging it into your predicate, and making sure that you get a true value out. And that process of taking each number, plugging it in, verifying that it works for that one number, going on to the next one, plugging that in, making sure it works, and then going through that and working through all the numbers is known as the method of exhaustion. Just like we're all sick of being trapped inside from this coronavirus. But you may see this phrase coming up either in this course or inside of your textbook or just in subsequent math courses if you go on to take them. The method of exhaustion is just verifying every single possible case, verifying every value in your domain to make sure that it satisfies the predicate. The second quantified statement is actually false because we can come up with a counter example. I can find some x value such that when I multiply it by 3, I get something greater I'll get something less than or equal to 5. For example, if I take 0 and I plug that in for x in 3x, I get 0, and 0 is not greater than 5. Also, -1 would also make the predicate false as well. But we have at least one element in our domain that makes the predicate false. Therefore, the second universally quantified statement is indeed false. So again, just as a quick recap, for a universal statement to be true, every x value in the domain has to make the predicate true. If even one x value makes the predicate false, then your universally quantified statement is false. Moving on, we're going to stick with the same numbers in our domain. This time we have, again, two quantified statements. Now, these both contain the existential quantifier. So one reads, there exists x in D such that x squared is equal to x. And 2 reads, there exists x in D such that x squared is less than 0. Just as a quick recap, to show that an existential statement is true, you just have to show that there is one value of x such that when you plug it in, it makes your predicate true. It doesn't have to be more than one. There very well may be more than one, but you just have to show one. In order to show that an existential statement is false, you'd have to show that every value in your domain makes the predicate false. So we're sticking with the same domain, -1, 0, 2, 3, 5, and 6. It shouldn't be too hard to see that the first quantified statement is true. We can find at least one x value, and in this case there's only one x value, which is 0. such that if you take 0 and you square it, you get a result that's equal to the number that you squared. 0 squared is equal to 0. So 0 is in our domain. It makes our predicate true. Therefore, this existential statement is true. The second quantified statement is false. Because if we were to substitute every x value that's in our domain into our predicate, the predicate would be false in every single case. When you square a whole number, you get something that is greater than or equal to 0. You never get something that is strictly less than 0. Therefore, there is no x value in our domain that makes our predicate true, which means that this existential statement is false. And then last set of quantified statements we're going to look at, these both involve the unique existential quantifier. Number 1 reads, there exists a unique x in D such that x squared is greater than 0 and x is less than 0. Number 2 reads, there exists a unique x in D such that x squared is positive and x is positive. Again, we're sticking with the same numbers in our domain, -1, 0, 2, 3, 5, and 6. First one, if you think about the numbers that we have inside of our domain, the first one is indeed true. Of all of the 6 x values that were in our set D, there's only one value that makes our entire predicate true. Our predicate in this case has 2 pieces to it. And since it's the conjunction of those 2, because we have the and showing up there, this number has to satisfy both conditions individually, and it does. The one x value that works for us here is x is equal to a -1. Take -1 and square it, you get +1, and -1 is indeed less than 0. And there is no other x value in there that satisfies both of these 2 pieces of our predicate. So there is only one x value that will make this true. Therefore, this unique existential statement is true. The second one is false, because if you look at our set capital D, we have 4 numbers that are positive, 2, 3, 5, and 6. For every one of those positive numbers, x squared is positive, its square is positive, and every one of those numbers themselves are positive. So for number 2, there is more than one x value that makes our predicate true. So while there exists an x value in D such that this is true, there does not exist a unique x value. There's not only one guy. So that's why we have to be careful and really note that exclamation point that follows our existential quantifier. So this was a bit more practice and a little bit more of an introduction into predicates, what these things look like, the substitution of values to see when they're true or when they're false, as well as each of our 3 quantifiers, how they get used, and determining whether or not these quantified statements are true. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.